All right, guys, so we have a few series of lessons that will talk about equilibrium, torque, rotational motion, kind of all putting those ideas together. So again, there is a little bit of overlap with what we talked about before, but kind of putting it all together to really understand torque, which we'll get to in one of these lessons. Before we do that, we want to do a little bit of a review over the idea of equilibrium. All right. So, to start with a simple example here as we talk about translational equilibrium. We have a 20-gram object suspended by a rope as shown. What is the net force? Okay, a couple things here. We have a force holding it up. That's going to be our force of tension. Obviously, we also have the force of gravity. The fact that it is suspended, right, it's not moving up or down, it's certainly not accelerating. That must mean that force of tension minus force of gravity equals 0. Force of tension equals force of gravity, which means that our net force is 0. Okay. All right. Similar example, although in this case, our box is being lifted at a velocity of 4.9 meters per second. What is the net force acting on it? Now, in this case, it may seem a little bit like that there would be a net force because it's being lifted and it is in motion, but the reality is, all right, we still have the force of tension, which is lifting it. We still have the force of gravity. And while it is moving, we can assume, because it doesn't mention that it's speeding up, slowing down, or accelerating, that this velocity is constant, which means that our force of tension is going to equal our force of gravity. So our acceleration is 0. Therefore, our net force is also 0. All right. So in both cases, the net force on our objects is 0. That means that these objects are in what we would call equilibrium. If the object is stationary, so think about yourself sitting in a chair, a book sitting on a table, we could say that it is in static equilibrium. If it is moving with a constant velocity, so think our planet, a plane that's cruising altitude, a car on cruise control, right? If it's moving with constant velocity, we could say that it is in dynamic equilibrium. All right, in both cases, the object is in translational equilibrium. Okay, and we're talking about translational. This term refers to motion along a line or an axis. Therefore, we have a few conditions. So first off, if we're in equilibrium, then a sum of our forces should equal 0. Right? Our net force should equal 0, which means that our net force in the x direction should be 0. And our net force in the y direction should also be 0. All right. So in this case, we have a little example here, right? If we have a sign suspended by ropes, so this could be a sign, this could be a traffic light, whatever, right? Now, if the tension in, let's call this one, tension 1, is 100, what is the weight of the sign? Okay, now we're missing a few things here, so I'm going to kind of fill in some of these blanks. And you can try solving this first by pausing and then trying to solve. So first, we'll call this T2. I'm going to give you guys a couple angles here. So let's say that this angle is 55 degrees. This angle is 25 degrees. All right, so we know T1 is 100 newtons. all right, we can go ahead and solve. So pause your video, then go ahead. All right, so if you're back, we can go ahead and break this down. There's two different strategies we can use to solve a problem like this. So our first strategy is the components. So in this case, we want to choose a point in our system that's in equilibrium, right, with all forces acting on it. In this case, we can use the intersection, right, where all the forces are intersecting. Okay, and then we're going to draw a free body diagram. And we want to break these forces into separate components, our x and y components. And then we're going to use the first condition. All right. So, a couple things here. All right. Each of these forces, so T1, T2, right, we can break down into its x and y components. I totally missed it, but you can't get the point. All right, so we got T1x, T2x, T2y, T1y. This is T1 equals 100. All right. So I broke it down into some components. So first off, we know if we look at our forces in the x direction, so T1x and T2x, so our total forces in the x direction would equal T2x minus T1x, which is equal to 0, right? Which means that T2x equals T1x. Now, this means that we just need to solve for one of those. So obviously we know T1x. So let's kind of break that down. All right, so we know that T1 is 100 newtons. We know that the angle is 55. T1x, T1y. All right. Now, we know that T1x, right, this is going to be our adjacent side. So T1x, pretty much always using kind of the same general trig functions. So T1, which is 100, cosine our angle, getting about 57.36 newtons. We can do the same thing for Ty, right? In this case, our y component of this force is the opposite side. So T1 sine 55, plug that in, we're going to get about 81.92 newtons. All right, so here, we know that each of these is going to be approximately 57.36 newtons. All right, if we were calculating the other side, we would get that too. All right. And then break down T2. So this is T2x, T2y. Now we know in this case, for T2y, we have our angle here, 25. We found T2x. Now what we can do is we can use our tan function to find Ty, right? Because we know T2y is going to equal, let me start this over. Talking about our tan function, I know that tan, our angle, is going to equal T2y, right, our opposite, over our adjacent. Because I know my adjacent, all right, T2x, tan 25, so T2y is going to equal 26.75 newtons. All right, now this is important because I need to know the y forces on this, because ultimately what I'm trying to find is the weight of the sign, right? I don't know the mass of the sign, obviously I don't know the weight, so it's important for me to know what are the components in the y direction, and that will help me solve for that, since this is all in static equilibrium. Okay, so I ran out of space a little bit, so I'm going to write here in this bottom section. So I want to know, right, what are my net forces in the y direction? So to figure out my y, right, I have the two cables, so T1y plus T2y, right, are holding the sign up. So I'm going to subtract the force of gravity of the sign. Right, these are all in equilibrium together. So what this means then is that T1y plus T2y equals Fg, right? The two y components of this two cables are holding up the gravitational pull of the sign. So now I'm just adding together the numbers that I calculated. So I know T1y is 81.92, T2y is 26.75, which equals about 109 newtons. That's going to give me the weight of my sign. If I wanted, I could divide that by 10 to find the mass of the sign. All right. So that is the components method of calculating kind of the forces acting in a problem like that. All right, strategy 2, we'll be looking at a closed vector diagram. All right, so key thing here, if our net force is 0, then that essentially means that all of our vectors added up are going to add up to 0, right? So all our vectors, they add up to 0. That's our key point, right? So what that means, if we have a net force of 0, all our vectors are going to add up to 0. We can use our sine law or cosine law, or you can be a little bit creative, to solve for the different sides of our triangle. Right? Kind of key thing here in the difference is we can never assume that our triangle is going to be a right angle triangle unless we can prove it geometrically. Right? So, going to take this little example here. So, a couple key things. We have a 64 Newton mass that's suspended, right? And our goal is to calculate the tensions in T1 and T2, and we're given some angles here. Right? So I have, that's way off. Okay, so I have T2. I have T1. And then I have my mass here. All right, now we're given that is 64 newtons. All right, so what I'm going to do is I'm going to kind of add up all these vectors together. So I have my mass here, which is Fg. I have T2 over here. And I have T1 over here. All right, so now what I can do is I can start essentially adding the things that I know, right? So the only side that I know is going to be the hanging mass, right, which is 64 newtons. The only other things that I'm given are some of the angles between our cables and just like the horizontal surface that they're attached to, right? So let's establish a couple things. So let's look at T1 first. All right, so I know, right, if I draw a horizontal line here, let's indicate that this is kind of a dashed line. All right, I know that the angle made here is going to be about 35 degrees. All right, I also know geometrically that this angle down here, right, is also going to be 35 degrees. Again, this is just your basic geometry. I know that gravity always pulls straight down, which means that the angle between this red vector and the horizontal is going to be a 90-degree angle, right? So just by basic subtraction, I can figure out that this angle here then, if we're to complete it, would be about 55 degrees. All right, and we can do the same thing for T2. So I can establish that the angle made here at the top on the exterior, right, is going to be 50 degrees. All right, I'm giving that over here. All right, so now I have a couple things I can do right now. I can use kind of that same method and just figure out, okay, this is also going to be a 90-degree angle, which means that this is going to be 40. Then I can kind of determine, okay, so I know that the three angles of my triangle are going to add up to 180. So 40, 55, I know that this larger angle is going to be 85 here. I could also use that same method, and I could have figured out, okay, if this angle here was 50, then this one was going to be 50 as well, right? And then those both add up to 85, right? So there's two different ways I could have figured that out. All right, so anyways, I now have the three angles of my triangle. Keep in mind, it's not a right triangle, so I'm going to have to use either sine or cosine laws to kind of solve for my missing sides. All right, so again, these are just some basic geometry skills. We haven't spent too much time on these ones, but these should be pretty familiar to you. All right, so let's start by solving for side T1. All right. Okay. So T1, I know that this, right, we can look at the opposite side, so the sine, all right, T1 over sine 40, right, which is the angle of that opposite side, is going to be equal to, let's use our side we know, FG over sine 85, which is its opposite side. Right. If we solve for TI, equals FG sine 40 over sine 85, TI, or T1, equals about 41 newtons. All right. And we can do the same thing for T2, right? Just using our sine law. All right, so T2, its opposite side is going to be sine 55. It's going to be equal to FG, also over sine 85. Just kind of ends up being the same thing. FG sine 55 over sine 85. And then T2 is approximately going to be 53 newtons. All right, and we're done. All right, so that's one more method of how you can solve for the different vectors in a problem like this in objects that are in equilibrium. All right. Let's take one more look at an example problem, and here what I'd like you to do is, again, pause and then try both methods, right? Try solving this with the trig method, try solving it with the component method. I'm going to kind of go over both here. Okay, so we have a trig method. And then we have my component method. All right. So I set up a section for both methods here. What I have here is I have objects suspended, right? Tension in one of the ropes is 50 newtons, right? That's T2. Try to figure out what is the weight of the object. So again, I know that this is at an angle and all these vectors are at equilibrium. So yeah, let me just kind of signify what we got here. Vector T1, T2, and FG. Okay, so let's start with taking a look at T2, because this is one that we have the most information about. So starting with the trig method. Okay. So we got T2. We know here that we can break this down into our X and Y components. So we got T2Y, T2X. I know that my angle here is 37. Okay, so T2Y is going to be equal to T2 sine 37 is going to equal 30.1 newtons. All right, and then I know that my force of gravity, right, is going to equal, actually, let me go backwards real quick. All right. So keep in mind, Well, I have the force of tension Ti, or T1. Notice that it is pulling 100% in the x direction, right? So it by itself is not pulling the y direction at all. The only thing kind of holding or working against the force of gravity is the y component of T2, right? So we're talking about the sum of forces in terms of holding the block up. We can pretty much ignore Ti for right now, right? So if we're talking about our net force, we know that the net force is going to be the y component of T2 minus gravity is going to equal 0, which means that Fg is going to equal 2Ty, which means Fg equals 30.1 newtons. Don't really need to do anything more than that. Again, it's asking for the weight, not the mass. If we want to know the mass, right, you just divide that by gravity. So, pretty straightforward for the trig method in that one. And that one was deceptively easy. All right, we can also work this out in the component method. So in this case, right, we can draw all three of our components. Now in this case, we can draw out a right triangle, right, because we get T2. We have Fg. And then we have Ti. And this only works out to be a right triangle because Ti is horizontal. All right, in this case, remember that our angle is 37. We know that this is 50. Okay, again, in this case, we're just trying to find Fg. So this just becomes a very simple trig formula because we have a right triangle here. Doesn't get very complicated. Right? So in this case, right, we know that we get Fg would be sine 37. It's going to be our this length divided by T2, so opposite of our hypotenuse, which means that Fg is going to equal T2 sine 37, which you can see is what we got in our trig method. It's going to equal 30.1 newtons. Okay. You know what? I totally mixed this up. Okay. This was trig. This was component. All right, two different ways to get the same answer. So you kind of use whichever one's going to work better for you. Again, if it's not a right triangle, pretty much going to be easier to use the component method. If it is a right triangle, trig method tends to be the simplest. That is the end of lesson 1.